Hi there, I'm Ricardo Flores, and we are with Cody Kenny at Evergreen Engineering Incorporated. Maybe just tell us where we are and a little bit about what you guys do.
Yeah, we're located on the northwest side of Eugene, and we are a multidiscipline engineering firm, and we have civil engineers, mechanical engineers, electrical engineers, chemical engineers, and environmental engineers here. And we work primarily in the industrial markets. We do a lot in the wood products industry. We work in specialty metals. We work in biomass power generation, work in chemical industries and for equipment manufacturers that make industrial equipment, and also in kind of the wood pellets energy industry. So lots of different industrial environments.
Wow. And how long have you guys been around?
We started right here in Eugene in 1985, and we now have office in Atlanta, Georgia, and one in Everett, Washington as well.
Huh. Okay. So why don't you go ahead and take us around? We'll take a look at this place and learn a little bit more about the jobs here.
Sure. Well, let's head out this way, I guess.
Okay, so when we're walking through here, I know students would probably like to see what this looks like to work in a place like this.
Sure.
Maybe you could just show us as we're headed to our next speaker.
So we're generally laid out with kind of offices around the perimeter for some of our managers, and then cubicles on the interior where we have designers and drafters and engineers working. And they generally are working on computers with multiple screens, but we also have lots of drawings that we print out and put them down on tables and redline and work on them that way.
So that's what each one of these is then?
Yeah,
as
a separate workspace.
It's like a shared workspace that they can have the drawings down?
Yep,
okay.
Yep. So I have Derek Seibert here. He's a professional mechanical engineer, has been with Evergreen for a number of years. So you can elaborate on that, and I'll let you chat with him.
Hi. As Cody said, I'm a mechanical engineer by trade, went to Oregon State, and basically this has pretty much been my job for the last 16 years. So I'm a lifer or a long timer at Evergreen. So the company's not bad, but pretty much mechanical is one of the broader subjects in one of the broader disciplines. So I do anything from machine design to thermal fluid heating, piping, and power systems, to some good old-fashioned HVAC design. So kind of a broad array of things, and started off doing some drawing and drafting and maybe a little bit of coffee making, and then eventually started training for my engineering license, and did that, and now I'm licensed in 4 or 5 states, depending on what projects we have going on, and doing all sorts of design for utilities for our manufacturing or industrial manufacturing clients. It's fun and challenging, and get to work in a bunch of different kind of quirky industries and some more straightforward ones.
So I'm thinking about, so this is for high school students. So, and there's a ton who are thinking, engineering, but as I'm learning, there's a lot of different engineers. So what's a path to get to, like what would you say a high schooler should be doing, sort of, and then the path they could go to become what you're doing?
Yeah, so I think the broadest, simplest version is having an understanding of math helps immensely, and understanding problem solving helps immensely. But the way I always kind of joke about it is when you were younger and you were doing math and maybe some physics and stuff like that, solving a story problem is kind of like what we do. Except we do it like here, it's like you get a phone call from a customer saying, can you solve this train collision problem in 20 minutes and make sure that it's super safe, and you learn. So a lot of it really is about what took me the longest time, even when I was in engineering school at Oregon State, was combining the disciplines and not getting so bogged down in the details with each one, but putting them, kind of synthesizing them together. So having a good understanding of math and algebra and stuff like that, but then also saying like, okay, what assumptions can I safely make here to solve this problem, and what can I kind of ignore and put aside for now, remaining calm. It's like everybody hates taking tests, and I feel like when I finally got good at engineering was when I got calm about them. And a lot of it's just knowing, what to tackle on a problem. And actually a really good summary of it was in the movie The Martian with Matt Damon. At the end of it, he just said, engineering is like solving one problem at a time and focusing on that one thing before you can move to the next step. And I think that's right. Take a problem that could be really complex and focus on the simple starting point, and then work your way to the next step, no matter how perilous or scary it may seem. So.
And then your degree, what took you? Is it 4 years? It's a 5 year?
They say 4+. So basically, it took me 4 years and 1 term, but my last term I kind of saved some electives for some fun at the end. So I took a guitar class at the end. But so the main core of the degree took 4 years, if you were taking quite a bit of credits, and a lot of people finish in 5. So just depends on your workload.
All right. Thank you for your time.
Yeah, so as Derek was just telling us that, you go to school and work your way through college, and that's generally 4 years. In there, you have a couple different options in that, you can work part-time at whatever job you can find, but there's also an internship program for the Oregon engineering schools, all the public ones, Oregon State, Oregon Tech, Portland State, and University of Portland are all in the program. And it's an internship program that's been around since the early 70s, and it pretty much covers all of the engineering disciplines and more. It even has some business degrees involved in it now. Wow. And that program is the junior and senior year of their in college, but you apply to get into it in your sophomore year of college, and you go on 2 full-time 6-month paid internships. And so you take time off of school. So basically it adds about 2 terms of school onto your duration that you're going. But you get a full years of on-the-job experience doing real engineering work. And so Evergreen's a part of that program. And I actually went through that as a civil engineering student at Oregon State. I was the first class of CCOP, which is kind of a branch of MECOP, but that was 20 plus years ago. So. Wow. And so I'm involved in it. I've been on the board of directors this last 2 years for the program, and it's a great path for engineering students to get some real-world experience, and it makes them very marketable when they graduate. Well, we're now here with Andrew Eckner. He's a designer drafter for us, and has been with Evergreen for a number of years. So, Andrew, I'll let you kind of tell them about your job here and your background.
I've worked with Evergreen for 11 years. I'm a designer draftsman. A lot of my time has been spent on client sites, helping them manage their drawings, and almost as an archivist, hey, we're looking to build something in this area. Can you help me find out what is there now, what's under the ground, sort of stuff like that. Has been a lot of what I do. In the office, I've been working with Cody and a number of the other engineers, trying to bring clients' ideas into, well, here's what we can do, that sort of
vision
thing.
to reality, as we like to say.
Exactly.
Yeah. So this is going to be for students, and a lot of different schools are going to see this, and they all use different software. So it sounds like you're a drafter, right?
Mostly, yes.
Okay,
yes.
and what sort of software do you use to do the drafting for these different projects?
A lot of it's AutoCAD. We also use Revit fairly extensively. Those are the main two that I have a familiarity with.
Okay. And what kind of background? Like, what was what's the path to get to become
I actually went to school in mathematics and am self-taught in AutoCAD. Had a computer that had a copy on it early on. I did in high school, did some drafting on a board in a woodshop class. And really enjoyed doing that. And so, like I say, I had a computer, and I'm like, oh, hey, this is really cool. And I found it really interesting to do, and so, like I said.
And now there's some good community college programs. Lane has one, for example, and it's a 2-year drafting technology degree. And they learn multiple different programs from Revit and AutoCAD. Also, maybe Inventor is a 3D modeling program, and another one we use here that's not taught in the community college, but it's called Plant 3D, and that's for the piping and mechanical design systems.
Okay, all right. So for your job, what are some skills you think students at the high school level could be thinking about and working on so that they could go to a track to do something like you're doing?
Attention to detail. I mean, just as a basic life skill, that would definitely be a good one. I'm strong in mathematics, geometry, You know, those things. Oh, I'll never use this in the real world. Yeah, you will.
Yeah.
You will. You know.
And it sounds like, I mean, I don't know that much about it, but so they have an idea of something they want to build, and then you draw it out for them so you can see structurally how it would be designed. Is that sort of how what you do?
Yeah, yeah.
Huh.
You know, it's like conveyors and things. It's like you can go to a certain angle before you start getting slippage, and it's like, well, can we do this in the space that we need?
Yeah.
You know, or are we going to have to make two laps in order to get where we're going? Equipment layout. Can I fit what I want in this space, or are we going to have to move it, you know, somewhere else? Something else I use in AutoCAD is it's a auto tracking thing to where you know, it's like, well, a turn radius on a truck. Am I going to be able to get off of that ramp and onto that scale? Is that even possible in this space? Stuff like that.
So in my mind then, even as I look at around here, it seems like no matter what, everything that's built probably has gone through drafting of some sort. Would you agree? You think that's true?
Yes. Yeah, for sure. I mean, you know, back into, like I said, in another position off-site, it was for Evergreen, but on a, you know, contractor site. It was started in the late 40s, and even then, it's all drafted up. You know, it's all engineered, obviously by hand. You know, with slide rules for calculations as far as, you know, things go. But yeah. Most things I believe in the world today are, you know, drafted somehow, designed at least.
Seems like a good skill for all of the different trades to know about.
Yeah.
Okay, Cody. So we've talked to a few people, and we haven't seen a lot. So maybe you can show us a little bit about some of the stuff that you guys are working on.
So here's just one example. So in an industrial plant, sometimes you have great big fans, and they're pushing air through the ventilation systems or the scrubber systems that are in the industrial processes. And so this particular drawings I just happened to walk by and flip it open to is the concrete foundation that holds up one of these massive fans. And so the engineer, we're going to go talk to a structural engineer here in a little bit, but that structural engineer got all the information about that fan, figured out how heavy it was and what the operational loads are when they start up, they want to move. And so the foundation has to hold it in place. And then obviously there's seismic to consider about. If it's a lot of mass, it starts shaking, the foundation also has to hold that. And so this drawing here is showing the different details to the contractor on how they're going to build that foundation. And so we've got a plan view here that gives them all the dimensions of it in looking down on it, is what plan view means. And then there's sections. So a section is like if I cut a slice through it, this is a section looking through the foundation, and all these big thick black lines are the rebar that's inside the concrete. And so the structural engineer may have taken a little hand sketch and kind of drew this up and then given it to somebody like Andrew, who we talked to, and they put it into a drawing that is all to scale. It's annotated to our standards, and it's has all the detail information that a contractor would need to build that foundation. And so that's kind of true for all the different disciplines, whether it's mechanical and you're doing a piping system, you're going to draw out all the pipes and label all the elbows and how far things are and where the valves are at. Or in an electrical system, it might be the conduits and specking out the wire sizes and how big the breakers are and things like that.
So this makes me feel like if I was you and I was an engineer, everything I looked at, my mind would be deconstructing it. Do you find that you do that? Like I look at this and think about, earthquakes and structural buildings.
My wife walks around looking at the landscape. I'm walking around looking like this up at the buildings. Especially, if I'm in a big city, looking at the overpasses, or you're in a parking garage, I'm always looking at how it's built. Yes, I do that a lot.
Well, the weight of building something, I don't know if you feel a lot of that weight or not, because you have to know down to every bolt.
You do.
It looks like every piece of rebar that structurally builds the foundation.
You do, and so there's a lot of, as an engineer, once you become a professional engineer, there's a responsibility that you have in that, and you place your seal on it when that drawing's ready and then you're responsible for that design.
So it goes back to attention to detail, proofreading,
and ethics.
Gosh,
and
I would
lots of
imagine
things.
communication, ethics. We didn't even think about ethics in that one.
So that's why the path to becoming an engineer takes a while. You got to go to school for 4 or 5 years, and then you have to be an engineer in training for 4 years underneath another PE doing engineering type work, and then you take a test, an 8-hour test to become an actual professional engineer. So we're here with Ella, who is a recent graduate, actually, of the Lane drafting program, and she's working on a CMU, which means concrete masonry unit building, that is generally used in our industries for electrical rooms. We put all the electrical power distribution equipment in this type of a building. And so it's like out, you'll see the stacked block buildings. That's what CMU is. And so she's kind of got a 3D view of it up there on her left screen, and then she's working on the different views of for the drawing, for the plan, and the wall elevations showing how the wall is constructed.
This is an engineering firm, but I feel like I'm in the library. So what are we looking at here, Cody?
Well, it's actually our engineering library. You put it right together. So, there's a lot of different reference information that we have, but also a lot of codes that we have to follow in engineering. And so I'm standing kind of in front of our building codes section. And so it's the different versions of the Oregon Structural Code, the Oregon Mechanical Code, the Oregon Fire Code. And then we have other states too, because we work all over the US. We have California, and we have different versions of codes that we use. And then additionally, there's all the different materials that we engineer. So there's a whole bunch of books on concrete right here, and then we have, a bunch of steel design books up here, and so there's different ones. And then also for those are all kind of structural related, and then we get into more mechanical stuff down here with boiler and pressure vessels and piping, and some general material reference type books. And granted,
Oh, sorry, go ahead.
well, a lot of this stuff is more available online now, but with the codes and the reference materials, sometimes really having a paper copy still is very usable, and I prefer it still, and a lot of people do.
Yeah. So students aren't going to know what codes mean. So what do you mean by code? Because
Yeah, that's a
everything you
good
do probably
question.
has to go by code.
That's right. So, say for a building, there is a set of rules essentially that have been developed over a long period of time to make sure that building is constructed safely. And so it's how big does the door need to be? How many doors do we need to have in there? How much weight does it need to be able to hold up for snow loads? And how much wind design pressure does it need to resist? And if I'm going to make it out of steel, what's the requirements for designing all that steel structure, and how it goes together, and what's its strength requirements? So the codes are really the kind of the rules that we operate under, and then we have latitude within those rules to figure out how we want to make the design work. So I have Jennifer Briggs here. She's a civil professional engineer, and we're in the structural department. And so structural engineering is really a specialty of civil engineering. And maybe I can let Jennifer kind of explain what civil engineering is and the different branches of it.
I need a dissertation.
So yeah, there's structural, which is what we here all do. Civil engineers can do planning roads, water, culverts.
Land use planning, like for subdivisions, traffic engineering. That's all falls within civil engineering, and so does geotechnical engineering as a branch of civil engineering. It's just a specific slice of it.
Which is soils and foundations.
Yeah.
We design foundations, but we hire geotechnical engineers to give us the soil properties to use in our foundation design. So
Wow.
kind of separate.
Yeah.
Most people do one or the other, not both.
Yeah.
Right.
And some of the stuff that you have up here, though, that looks totally different from what I was just thinking about. So what is this
so
maybe?
we do structures. So these are structures, and we do industrial structures. So this is an example, and if you see over here, we've got a cyclone, which is just a steel cylinder, cyclone shaped, and some ducts coming out of it and some ducts coming into it. So that's designed by someone else. What we do is we design the platforms, the steel support to support that structure, and to provide access to it for, maintenance or however someone needs to get to it. So in this case, this is a 140-foot tall tower. We model it up, put all the members in there, load it up, wind loads, seismic loads, gravity loads, meaning the weights of the equipment and everything you expect to be on the structure. And then we can use this program, this is RISA, to run the model, run all the loads on it, and it'll tell us where we're seeing failures. It'll show us where things are moving more than we want them to move. It will give us reactions so we can design our connections and our anchorage to the foundation.
So it literally runs a test, like you say, wind 10 miles an hour from the east, and it.
Well, no, that's so for I will use this. This is MathCAD, and this is where we actually do math. So I will say.
Look at that math.
Yeah, there's
Yeah.
actually
Look
math
out,
in there,
students,
students.
I see math.
I know.
So I say my wind's 10 miles per hour, and then I go through all these equations to get what the force is on each piece of equipment and steel on this tower, and then I put those in here as forces. So
this sounds like physics. I mean, did
Yeah.
you have to take a lot of physics in order to?
Yeah.
yeah, so these are so I'm loading each beam. I'm loading each piece of equipment.
So back to the code that we were talking about. So the building code says for Eugene, Oregon, our design wind speed is 95 miles an hour. And then there's another standard, or it's called ASCE 7, which stands for American Society of Civil Engineers, and that's the
There it is.
prescribed building code loads. And so you take your wind speed, and then you develop these loads she's talking about for your structure,
Huh.
and then you apply the loads to the structure.
Wow.
And it has a bunch of other, factors that you apply depending on what kind of structure you have, depending on if it's a square or if it's round, how far above the ground you are.
Huh.
All
Okay.
of those. are taken
So what
into
kind of
account.
path do you take education-wise to become what you do?
So I have a master's degree in civil engineering. Don't need a master's, just a bachelor's degree, but you would need a bachelor's degree in civil engineering. And then, and then you would take the EIT exam when you're still in college or right after you graduate, then you become an engineering intern. And I think you probably already talked about this with the
Is
other
that a
engineers.
little
It's
bit
the same
you're talking
path.
about? Then you work for a little while, and
Then you work for 4
Yeah.
years.
Okay.
Yeah, and then you take your professional engineering exam.
Right.
Okay. Any suggestions for classes students could take that would maybe prepare them for something, to go into a career like this, develop some of those skills?
In math, definitely math.
Yeah.
Lots of math, physics. Anything problem solving. It's a lot of problem solving. We don't like to say, no, we can't do that. It's going to be really expensive to do that, but we can generally figure out a way to do something if someone wants it done. Or suggest a different way that might work better.
Okay.
But, so.
Professional skills they could be working on? What do you think?
Communication. Communication is always important, both written and verbal. Being able to write an email with proper grammar and to get your point across.
Yeah.
Being able to work with the team. I mean, we work together. There are very few projects where you don't work with someone else in the office. So being able to work with others and being able to communicate.
All right, so I'm here with John Meshnick, who is an electrical professional engineer, has been with Evergreen for a long time. I'll let him elaborate on that. And John, you want to introduce yourself and tell them a little about your
Sure.
background?
I'm John Meshnick, and I've been here for 30 plus years. Came here in 1989. Went to school in Montana State, got a second degree from there. I was what's known as a kind of a non-traditional student at the point in time. Had a family and changed careers and came here. Been here ever since.
So you're when you say you're schooling because you're an electrical engineer, so that's your specific path that you did to that. Is that what you mean?
Yes.
Or it's an undergrad and a graduate. How does that go?
Well, it's a undergrad, basically a 4 or 5 year program, depending on what kind of a schedule you're on. And in my particular case, I went through their electrical engineering program. At that point in time, and I think they still have it, is an electrical tech program, which is not quite so mathematical based of program. It's less calculus is associated with that particular type of a program. And so I was in the electrical engineering and then came here. And after so many years of experience here, then I was able to test in and become a professional engineer.
And what exactly does an electrical engineer do? Like what's your
Well,
part?
in this particular case, there's a lot of different varieties of electrical engineering. In this particular case, we're heavily steeped in power distribution and control. We deal with processes that have to do with pulp and paper and wood products, that sort of thing. And so anything that's associated with that, all the way from conveyance to lighting, and maybe perhaps safety issues, like monitoring the environment, that sort of thing within the work environment. Those are the things we take care of. We also get into the commercial realm or the institutional realm, which would be the universities or perhaps a store or something like that. We don't do that a lot, but that is also an area where you would deal with power distribution in the terms of lighting and public safety and HVAC systems, the cooling, systems that are in buildings.
So anything that has to do with power that's going into a facility that you guys are building, that's what you're doing, like how it all comes in, how it gets distributed, and what happens.
That's right.
Okay.
We interface with the utility, and from the utility on in, we do the power design to make things happen.
So
with-
you do
within the
design,
building.
electricians then come in and actually do the wiring.
Correct.
those
They
things.
use our product,
Okay.
which is, a piece of paper like that with the various drawings on it, and they install with that.
Yeah, so another piece of this we haven't talked about yet is that in order to build a project, you have to have a survey of that. And so what that means is, before, this was a greenfield plant that we did all the engineering for. And when we were talking to Jennifer, she did those big structures. Well, those big structures are these little pieces in here. I mean, that's how big this plant is.
Yeah.
And but before they could build it, they had to come out and survey the ground to know where it was going up and down and what, its contour of the topography was. And then when we engineered all the plans, they had to come out and lay that out on the property. So I had to find the property corners and then go place the buildings on the plan so that the guys putting in the foundations would know where to place those and what elevation to put them at. And so a surveyor is a critical aspect to the construction world and the engineering world, because both of us need that information. And so one thing we're having in the problem right now is that not very many students are going into surveying, and it's a very good career. It pays well. It pays as much as most engineers get, but in the last 20 years, we've had a massive decline in the number of surveyors that we have in the profession. There's some data in 2000, we had about 2,000 registered professional land surveyors in Oregon, and we're down to about 800 now.
Wow.
And so it's something that we're trying to address at a professional level, but we really need to get the word out in the high schools that surveying is a really good career as well. It's technical. You get to do some field work, but then there's also office work.
Yeah.
So you can kind of get a variety of that. And there's some college programs to do that. Oregon Tech is one that has one. Also, if you go through a civil engineering program, you can specialize in doing surveying and then kind of do both, or just go down surveying path.
Is it a shorter program? Do you know what the program
I
entails?
think that there's a 4-year option and a 2-year path as well. So if you get the 2-year path, you're going to be more running the equipment for quite a while, but then I think over time with more experience, say 6 years instead of 4 years, you can take the test and become a professional land surveyor.
Okay. And those are the gentlemen and ladies that we see at sites or on the sides of roads with their...
Yeah, and they got the machine, the tripod,
Yeah, the
the orange, and
tripod.
they might be looking through it, or they're holding the stick up, and the machine's
Yeah.
over there, and
Yeah.
the new ones are using GPS a lot, and they're
Huh.
getting the same information, but instead of optically, they're using the global position.
And then with that, then they're drawing out. They would know the distance of and where
they
to put
might
the points of the
You've ever
building.
seen a contour map that shows the elevations?
Uh-huh.
They'll draw those contours on there and what the existing grades are.
Yeah.
And then they might, then have to stake out certain points. Like if I want to know where the corner of that building is on the
Yeah.
site, and this is just a flat field,
Yeah.
that they can go put a stake right there
Yeah.
and locate that point.
All right, Cody. So we really appreciate your time. Thank you so much. So maybe you could just tell us how, if someone wanted to work here, are there some jobs for students, or the best way to find out about those, and then anything closing thoughts for students?
Yeah, well, it's difficult because there's so many technical things you have to know to kind of do this job. We don't do a lot of internships at the high school level. I mentioned the MECOP internship program that we're in for the college level. But looking to get into the career, I'd really start talking to your high school advisors on that technical career path and what courses should I be taking now. It's really important to set yourself up in high school to start taking those math classes and working through as high as levels you can get in high school, and the science, all the science and math you can get. And then of course, don't slack off on communications. We heard multiple people say that we need those strong communication skills in writing and speaking and listening. And then preparing yourself to go down that college path. And I think the community college path is a great path to go. I did that myself, and it saves a lot of money, and you get in that first couple of years, you have all the same classes you'd be taking at the university level, but you do have a lot more close interaction with your instructors and helping you get through those calculus classes and the physics classes that are tough.
Yeah.
And but you can get through it. I wasn't the smartest kid out there. I just worked hard and I made it through it. So yeah, so just starting to get your path set down that trajectory is how you get into the technical field.
All right, great. Well, thank you so much for your time.
Yeah, you're welcome. Thank you.